Hassler here. I'm going to work through the 4.2 Explore and give you some notes on the back side based on the lesson that we are doing in class. And so in this particular problem, in math class, we solve lots of problems. There are some problems that don't have a solution? And we know the answer to that is yes. And there are some problems that have infinitely many solutions. And so we're going to continue to look at systems. We're looking at two equations at a time to determine when we would have no solution, infinitely many solutions, or perhaps just one solution. All right, so problem one says we'll start by looking at the line y equals 2x minus 5. And so it says give the ordered pairs of at least 4 points. And so we'll do this in blue. Actually, what I did is I decided to make a table. You know, in the first couple of units, we worked so much with tables, and I thought this would be a good place to bring this in. And you can start with any x value that you want. I think an easy x value to start with would be 0. And so if I were to substitute 0 in for x here, right, I would have 2 times 0 minus 5, and that would give me negative 5. And so I'm just substituting numbers in. I would do 1 next. I would do 2 times 1, which is 2 minus 5, so that's negative 3. And then I would substitute 2 in. That's 4 minus 5, which is negative 1. Substitute 3 and I get 1. And if you recall from when we did this back in Unit 2, notice that my y values are increasing by 2 as my x's increase by 1, and that matches that slope. That idea of my rate of change is change in y is 2 over change in x is 1. So just a little review. B says graph the line on the large axis on the board. So in class we had these really large magnetic coordinate planes so that instead of trying to squeeze it onto this paper, we could put it onto the coordinate plane. I'm going to obviously put it on this paper. Now I could either graph the points that I just found, or I could graph using this information. Either one. If I graph my points, I have 0, negative 5. I have 1, negative 3. I have 2, negative 1. I have 3, 1, and so on. Guys, when you graph your lines, go ahead and extend with some arrows, please. By the way, if I go back over here to my my information, this, again, tells me the slope. And I'm writing in yellow, sorry. And this is my y-intercept. And so if I look at my graph, I have a y-intercept of negative 5. And I do have a slope of 2. Up 2 to the right 1, up 2 to the right 1. And so I could graph either looking at the equation or looking at the table. Part C says, is the point negative 17, negative 39 on this line? Well, I can't really extend out my grid to negative 17 on the x-axis or negative 39 on the y-axis. You can just substitute this in and check it. In other words, if I put negative 39 in for y, and if I put negative 17 in for x, I'm going to put a question mark here. Does this work? So I'm going to type this into my calculator. And when I do, I get negative 39. And so yes, because that point works to make this equation true, this point would be a point on the line. It would be a point that I would put into my table. Okay. All right, so 2 says, let's consider the line y equals negative 1/2 x. I'm going to do this in a different color. We'll do red. So list some ordered pairs of points that are on this line. And again, I'm going to go back to my table. So I've got 0, and if I put 0 in, I get 0 out. Say 1, negative 1/2 times 1 is negative 1/2. If I put 2 in, I get negative 1. It just says sum, so I'll do my 4 points like I did before. Graph the line on the same coordinate plane using a different color. So I have red, so I've got the point 0, 0. Instead of graphing this one, I'm going to graph the one that has a point that I can actually use here. I noticed that, again, in my equation, I have a slope of negative 1/2. So I actually can just keep with my pattern of negative 1/2, down 1 to the right 2. Or from 0, 0, I could go up 1 to the left 2. There's no constant, which matches my y-intercept of 0. So this is great. And it says, are there any points that are on both lines? Yes. I have this point of intersection that we talked about in the last unit. If so, which ones? Well, there's only one, and it's at the point 2, -1. So that would be a solution. That would be a point that is true for both lines. It's that point of intersection. All right, let's see what we have in store here. It says, now let's think about the line 6x minus 3y equals 15. Find the x and y intercepts of this line. Okay, so an x-intercept, if you recall, looks like this. It's some number, comma, 0. So the y is always 0. And a y-intercept looks like this. It's 0, comma, some number. So x is always 0. So let's review. I'm looking for an x-intercept. That's when y is 0. So I got 6x minus 3 times 0 equals 15. I really just have 6x equals 15. And if I divide both sides by 6, I get 2.5. And for y-intercept, that's when x is 0. So let's calculate this one. I got 6 times 0 minus 3y equals 15. I really have -3y equals 15. And if I divide both sides by -3, I really get -5. I could go and graph those. And let's do that because, by the way, it's going to tell us to graph in a different color. And so let's see. For this, I have an x-intercept of 2.5. Well, that's not super helpful right now, but I do have a y-intercept of -5. Well, that's interesting because both of those points look like they're on my blue line. Okay, that's interesting. And let's go back down here. B says find the slope of the line. Well, I guess since both my points look like they're on the blue line, I could say that it would be the same slope as the blue line. But with that 2.5, I'm just not certain if I did this accurately on my graphing. So let's talk about how we find this slope, right? I have this equation, and if I could put this into that y equals mx plus b form, that would be great, right? If I want to isolate y. And so I'm going to run out of room, so I'm going to just try to do it here off in the margin. I'm going to rewrite. If I have this equation, 6x minus 3y equals 15, I want to get this y by itself. So to get that y by itself, I would have to get rid of the 6x. I'm going to subtract 6x on both sides. When I do that, 6x minus 6x is 0. We just have to be careful because these are not like terms. So I'm going to write 15 minus 6x. And then I want to get that y by itself. So I'm going to divide by -3. And we talked that when you multiply or divide, all parts get multiplied or divided. And so -3 divided by -3 is 1y, so that's helpful. 15 divided by -3 is -5, so that's helpful. And -6 divided by -3 is +2. Hey, I've seen this equation before. That is the same equation as this top one. It's just written in a different order. And so it turns out that this blue line and my green line happen to be the same line. And so are there any points, it says, are there any points on this line that are also on y equals 2x minus 5? All of them. Yes, all of them. Oops, I can't spell them, sorry. So I graphed the line already. What do you notice? It's the same as the y equals 2x minus 5 line. And then problem 4, let's see, we'll use orange for this. It says use a different color, got it, orange, to graph a line that shares no points. And what do you notice about the slope and y-intercept of this line? So again, I'm comparing this back to the 2x minus 5. I want to have no points in common. So it means I don't want to have the same y-intercept, so just go pick a different one. Oops, got to have a pen to do it. And if I want them to have no points, they have to be changing at the same rate. So they need the same slope, which was 2. I want them to be parallel. And parallel lines have that same slope. You could have picked your y-intercept to be anything else as long as it was not -5. And so it says, what do you notice about the slope and y-intercept? So we have the same slope so that they're parallel. I'll just make a note, parallel. But we had different y-intercepts because I want them to be different lines. So these are the big ideas. Big ideas are this. I can have 2 lines that intersect at one point. I could have 2 lines that are exactly the same, so there are infinitely many solutions or all real numbers as my solution. And I could have 2 lines that never intersect, so there is no solution. Matches up with ideas that we have talked about in the past. Okay, so let's flip over and let's take some quick notes. And so some things that I want to say in the quick notes is that a solution to a system is that point of intersection. And I'm just going to call that point of intersection x, y. Okay. I could have 0, 1, or infinite solutions. Okay. So let's talk about those different scenarios, right? So I could have no solution. I'm going to say SOL for solution. I could have 1 solution, or I could have, I'm going to say all real numbers instead of infinite. I'm going to use the number symbol. Okay. And let's just get some graphs to go with these here. So no solution would be when I have those parallel lines. And so I'm just going to make a note that these are parallel, which means that they have the same slope, but they have different y-intercepts. I'm going to abbreviate different. They never intersect, so there's no point of intersection, which means there's no solution. I could have 1 solution, and 1 solution would be if I had 2 lines that intersected each other at just that one point, okay? And so intersect at one point, x, y. And I could have infinite solutions, or we say all real numbers. And what happens with that is that I end up with 2 lines. And when I graph those 2 lines, they happen to be the same. And so they're the same line instead of being parallel lines. What that means is that they have the same slope and they have the same y-intercept. Okay. All right, so what I want you to do is I want you to take this information. I think you have enough information to try to check your understanding. I will have the answer key posted so you can check your work. If you have questions, let me know. And the homework is the 4.2 practice.